How is this possible at a distance of 11 billion miles from the Sun? The venerable Voyager 1 probe controlled by NASA passed the barrier between the solar influence and the interstellar medium on August 25, 2012. The primary purpose of Voyager 1 and 2 was to study Saturn and Jupiter. The first Voyager set off on a different trajectory to the solar system's edge since it was primarily focused on Saturn's huge moon Titan, while the second Voyager also visited Neptune and Uranus. Voyager 2's 1989 flyby of Neptune was the reason for the development of Voyager interstellar mission. Voyager 1, along with its twin, is currently undertaking innovative research and is still functioning strong, sending back data. Now, researchers are receiving worrying replies that reach the Milky Way's protected zones. What is happening to one of the most iconic space exploration devices ever made? Was that an unwarranted alarm? Join us as we study how Voyager 1 suddenly received an alarming answer from a close object in space. As Earth's first missionaries to the outer planets, the Voyager spacecraft fascinated the globe in the 1970s and 1980s by delivering up-close images of Neptune, Saturn, Jupiter, and Uranus. On August 17, 1977, Voyager 2 was the first to blast off into space, and on September 5, a few weeks later, Voyager 1 did the same. The Voyager twins act as living memorials to their time. In many ways, their data transfer speeds are roughly 440,000 times slower than 5G internet. They both have 3 million times less memory than modern cell phones and an 8-track tape player for data recording. They both have a golden record, a message from humanity to the cosmos with greetings in 55 languages, photographs of Earth and its inhabitants, and music spanning from Beethoven to Chuck Berry's Johnny B. Good. Although the missions have garnered little public attention in the last several decades, project scientist Ed Stone has overseen the continual investigation of the solar system by the tiny spacecraft. Linda Spilker, who has been involved with the mission since 1977, assumed Stone's post following her retirement. Being the sole instruments to ever transit interstellar space, the Voyagers continue to push the frontiers of space exploration, despite their now archaic memory and communication systems. The planetary encounters that made Voyager famous began 2 years after its launch in 1977, when the twin probes flew by Jupiter. Voyager 1 and 2 both visited Jupiter and Saturn before separating ways. Voyager 2 continued into Uranus and Neptune at a somewhat slower rate. Though the Voyagers wouldn't officially enter interstellar space until they left the heliosphere, the area surrounding our Sun, the Voyager interstellar mission formally began on January 1, 1990, and all planetary visits were accomplished within a decade. In August 2012, Voyager 1 reached the heliopause, commemorating 2 tranquil decades since it left the outer planets behind. 6 years later, in November 2018, its slower twin passed that border. The Sun is a nuclear explosion that releases high-energy particles all the time. These particles are flying through our solar system at dizzying rates, causing the Sun's influence to radiate far beyond the planets and finally clash with interstellar particles. The termination shock is the inner, roughly spherical barrier. The heliosheath is located beyond it. As Voyager 1 rushed past the heliosheath, the solar system's most remote neighborhood and what is considered to be the heliopause, its true limit, scientists had predicted that it would pick up on 2 unique signals. Thankfully, Voyager 1's and Voyager 2's vital instruments were operational, and the spacecraft's nuclear power supply kept it operating. For some reason, scientists could only establish the existence of one of 2 instances. According to scientific forecasts, Voyager 1 would no longer detect the solar wind, which is a stream of charged particles generated by the Sun when it fades away near the border between the solar system and interstellar space. Yes, that did occur. Additionally, they projected that as Voyager 1 departed, the magnetic bubbles encircling the Sun, the field orientation would vary. That failed. The natural world has a much better imagination than people. The spacecraft witnessed a temporary reduction in the strength of the solar wind. It weighs roughly 1,600, and according to NASA, could fit inside a cube that is 13 feet on each side. Excitement was the term that Edward S. C. Stone used to describe it. Such a dramatic decrease was unprecedented. It was completed in about 24 hours. It was back up and running 5 days after that. During the middle of August, there was a temporary and deeper downturn. Next, on August 25, the solar wind plummeted by a factor of over 1,000, eventually dropping to levels that couldn't be detected. Concurrently, there was a 99.3% rise in the number of extrasolar cosmic rays. We looked to be outside. Nonetheless, the field's continuous and unyielding orientation revealed that Voyager 1 remained caught in the Sun's magnetic field, where solar particles may be able to escape. Because the solar system's magnetic fields partially combine with those of the interstellar medium, according to astronomers' best predictions, the Voyager spacecraft has indisputably departed the heliosphere and entered interstellar space. Due to the high particle density there, the heliosphere is home to the solar wind, a stream of charged particles emerging from the Sun. At those distances, the density was 5 times higher than what we saw in the solar wind. The exact spike in particle density was measured by Voyager 2's detectors upon entrance into interstellar space on November 5, 2018. Though the probe's entry into interstellar space was clear, the heliopause, a twilight zone separating the heliosphere's bubble-like interior from interstellar space, exhibited characteristics that were not anticipated during their 2-month voyage. Each spacecraft transmitted data on plasma density peaks and valleys. We were expecting a beep, but the heliopause was deeper and more convoluted than we had thought. It's not like a line or a door. Nonetheless, it also serves as a barrier that enables communication. Data on magnetic fields obtained by Voyager 1 in 2012 and Voyager 2 in 2016 led to the stunning revelation that particles enter and depart the heliosphere. Plutonium-238, with an 88-year half-life, fuels the Voyagers. At launch, it seemed like an eternity, but now we're almost halfway through the half-life, and the spacecraft's working power is running short. With the completion of the planetary mission, the Voyager teams disabled a number of instruments, including the cameras. It was either switch off the instruments, turn off the heaters, or lose the spaceship. No one knew if the instruments could work without the heaters. Thankfully, even after the heaters were switched off one by one, the equipment carried on generating and delivering data. Older spacecraft also lack the transmission capacity necessary to send a strong signal back to Earth over billions of miles, so telescopes on Earth have had to work harder and harder to pick up their feeble signals. Ed likened it to a space-based refrigerator light bulb that blinks. We are referring to that degree of signal strength. Therefore, we must make extraordinary efforts to communicate with people on the ground. As the Voyagers continue to recede into space, we were able to maintain connection with them due to technological breakthroughs on Earth, such as the installation of 230T dishes for the Deep Space Network. It is a credit to the creativity of Voyager's engineers that the spacecraft continues its mission to bravely journey where no spacecraft has gone before. With a velocity of nearly 1 million miles per day, Voyager 1 has already departed the heliosphere by billions of miles, a distance similar to that of Neptune from Earth, and it continues to make remarkable discoveries. It is still exposed to the Sun's radiation even at that distance, as solar flares and coronal mass ejections make their way across the solar system. They can aggregate and merge into gigantic events that press against the heliosphere, causing ripples to ripple over interstellar space, and Voyager is able to note it because of its great distance from Earth. The Voyagers also glimpse the Sun and Earth from an altogether new angle. Voyager affords us a first-of-its-kind opportunity to see our star and solar system from an extraterrestrial perspective. For decades, scientists have researched other stars and collected remote data, but our knowledge of our own star has been restricted to what we have observed from the inside, if you will. The question then becomes, how do people see us? A spacecraft in orbit, or even better, 2 spacecraft in different areas of the galaxy, would be the only sure approach to find out. According to NASA, a computer failure has created a temporary communication breakdown between the 46-year-old Voyager 1 spacecraft and its mission team on Earth. As the battered spacecraft travels over undiscovered cosmic terrain towards the solar system's edge, engineers are desperately striving to find a solution. Among Voyager 1's three processes is a flight data system that aggregates readings from the spacecraft's scientific sensors with engineering data that represents the vessel's present health status. That data is delivered to mission control on Earth in binary code, which is a string of ones and zeros. It seems like the Voyager 1 flight data system is presently in a loop, like something out of Groundhog Day. When the telecoms unit of the flight data system started transmitting a backup pattern of ones and zeros, as if it was locked in a loop, the mission crew initially detected the problem late last year. Due to an issue with the communications unit, Voyager 1 is unable to relay any scientific or engineering data back to Earth, although the spacecraft may still receive and execute orders received by the mission team. There has been no usable data returned from the Voyager spacecraft since the researchers submitted commands. Over the weekend to restart the flight data system, engineers are now seeking to acquire more information regarding the fundamental cause of the issue before considering how to potentially fix it. Weeks may pass during the process. It does not appear that the present situation is related to prior problems that Voyager 1 has encountered in the past few years. The previous incidents of a comparable, but not identical malfunction with the flight data system occurred in 1981. Both Voyager probes are undergoing additional trials, and the mission team is left with nothing except the original instructions, which were written decades ago and don't cover the challenges the spacecraft are facing as they get older. In order to avoid any unintended effects, the Voyager crew is delaying to send further commands to the ship until they have thoroughly studied all of the possible ramifications. Because of how far away Voyager 1 is, Earth-sent commands take 22.5 hours to reach the spacecraft. On top of that, they have to wait 45 hours to hear back. In order to prolong the missions of the aging twin Voyager probes and conserve power, the team has been gradually turning off instruments on these senior citizens. As mentioned before by Voyager project manager Suzanne Dodd, Voyager 2 lost contact with Earth for 7 months in 2020 amid other unforeseen problems and dropouts experienced by both spacecraft. When a command mistakenly switched Voyager 2's antenna in the incorrect way last August, the mission team resorted to a last-ditch method to get in touch with the spaceship. The primary benefit of the mission is its length. Even if the crew is seeking to resume Voyager 1's regular data transmissions, extending the probe's travel distance from the heliosphere allows scientists to detect changes in particles and magnetic fields, for instance. However, data from Voyager 1 will be missing from that data set unless the spacecraft can contact Earth in the future. In order to maintain both spacecraft powered up and continue their record-breaking flights, the mission team has been getting imaginative with its approaches. In recent years, the Voyagers have continued to function for an unparalleled amount of time, considerably beyond the completion of their initial missions. Therefore, we predict that problems will surface, even though the engineering department is working feverishly to assure their survival. So where do the Voyagers go from here? As they enter the pure interstellar medium, the silent ambassadors will gradually become silent. As solar activity declines and atmospheric turbulence lowers, spacecraft will most likely capture interstellar stuff. Mission personnel have claimed that the two spacecraft are nearing the end of their operational lifespan, owing to running out of power. The last time scientists hear from them is likely to be in the 2030s at the earliest. Thanks for watching another episode of Mega Entertainment. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space. Though the probe's entry into interstellar space was clear, the heliopause, a twilight zone separating the heliosphere's bubble-like interior from interstellar space, exhibited characteristics that were not anticipated during their 2-month voyage. Each spacecraft transmitted data on plasma density peaks and valleys. We were expecting a beep, but the heliopause was deeper and more convoluted than we had thought. It's not like a line or a door. Nonetheless, it also serves as a barrier that enables communication. Data on magnetic fields obtained by Voyager 1 in 2012 and Voyager 2 in 2016 led to the stunning revelation that particles enter and depart the heliosphere. Scientists were perplexed by the data on heliopause magnetic fields acquired by the Voyagers. Since theory expected that the galactic magnetic field would be inclined to the solar magnetic field, A shift should have occurred at the point where the solar magnetic field and the intergalactic magnetic field collided. Voyager 1 and 2 did not pick up on changes in the direction of the magnetic field, though there was no shift in angle as Voyager crossed. In the absence of spinning, the magnetic field maintained an almost solar-like form. It remains a mystery. It's as if the heliosphere has these portals that particles can utilize to arrive and escape. It's likely to be a place where the magnetic field re-establishes itself. The heliopause seems to be the warped heliosphere surface that reacts to solar activity, albeit for what cause is still unknown. The amount of incoming radiation was approximately 10 times larger outside the heliosphere than inside the bubble, according to Voyager's observations. The Voyager mission proved that the Sun is collecting up to 90% of the interstellar radiation through its heliosphere and solar wind, which implies that astronauts are not directly exposed to this potentially dangerous radiation. In truth, the solar wind is safeguarding us from harm. Nobody recognized how heavily sheltered we were until the Voyagers arrived. Another surprising result from the voyages was the Sun's boundary interaction. Like two north magnets, magnetized plasmas cannot mix when they come into contact with one another. This means that solar wind or solar plasma cannot mix with interstellar plasma. However, there are also non-electrified particles in the universe that could care less. These particles would just ignore the heliospheric barriers and continue on their path. Both of these things eventually affect our solar environment, and our environment can do the same for them. Other missions, particularly IBEX and New Horizons, have supplied further information regarding the nature of these unique interactions in the heliosphere, which the Voyagers cannot directly measure. To enhance the deep but geographically limited data obtained by the two Voyagers, IMAP will launch in 2025 and offer a precise map of that elusive boundary zone. Now that Voyager 1 has reached $40 beyond the heliopause, researchers can finally learn the truth about the nature of the interstellar medium. It is discovered to be significantly more impacted by the heliosphere than previously believed. The Voyager probes have proven that the interstellar medium is not calm but rather agitated and impacted by solar winds. We still have no idea what's occurring, and it's completely different from what we imagined. According to the data, galactic cosmic rays don't act the same when they're directed either parallel or perpendicular to the solar magnetic field. Solar coronal mass ejections, which disrupt the Sun's magnetic field and reach into the interstellar medium, are a possible explanation for the data. The new way cosmic rays can reach Earth has scientists scratching their heads. At the same moment, scientists detected a frightening and bizarre phenomenon happening on the solar system's edge. The Alipec pores and interstellar media seem to be rippling and forming oblique angles in an unanticipated fashion. Although the theory that Alipec pores can and does change shape is not new, scientists have just lately confirmed that this is not the case. This finding was derived from information gathered by NASA's Interstellar Boundary Explorer satellite, which studies the emissions of energetic neutral atoms produced by the interaction of solar winds and the interstellar medium and collected by Voyager 1 and Voyager 2, the only spacecraft to have left the heliosphere so far. So far, the main inside-view direct measurement of these boundary positions has come from the Voyager spacecraft, but that was at a single instant in time and space. Based on the data, scientists have constructed models to anticipate future heliopause movements. A constantly shifting barrier is generated by the mutual dragging and pushing of solar winds and the interstellar medium. However, fresh information about the Alipec pores has come to light, which runs opposite to what was previously known. During a few months in 2014, IBEX recorded the illumination of the Alipec pores, which pointed to Alipec asymmetries. The researchers then noticed that these asymmetries did not meet the forecasts. In addition, scientists observed that the heliopause altered dramatically in a relatively short timespan when they evaluated data from Voyager 1 and Voyager 2 missions. That shed light on the cause for the substantial time difference between the two probes' 2012 and 2018 entrance into interstellar space, respectively. However, models also failed to account for that form of heliopause movement. The researchers classified these discrepancies as intriguing and potentially problematic. They intend to undertake further heliopause research in the hopes of acquiring further insight. With the debut of NASA's Interstellar Mapping and Acceleration Probe in 2025, an enhanced satellite capable of detecting energetic neutral atoms, all we can do is conjecture about this eerie solar system occurrence.